So hi and hello there, welcome to the new section of the course, and from this section we are going to see the AC analysis of JFET. So till now we were doing the DC analysis, and let me just quickly revise for what reason we were actually focusing on DC analysis. So we all know JFET is mostly used for what? JFET, it is mostly used for two purpose. It has two purpose, or rather whatever transistor that you use. Instead of JFET you might use BJTs or MOSFETs, whatever transistor you use. They are mostly used for two purposes, and they are as follows. That is, they are used as a switch, right? And or else they are also used as an amplifiers. Okay, we all know these particular things since we had already covered these particular things in course of bipolar junction transistor, right? So when it comes to amplifier, we need to bias JFET at certain point, right? Obviously at the middle of the transfer characteristic, if you could remember. Okay, at the middle of the transfer characteristic, and at the same time at the middle part of the this drain and source characteristic. Okay, so when I talk about biasing JFET, so what I'm talking about DC analysis. Why? Because DC analysis, with the help of DC analysis, we are able to see we are able to calculate what? We are able to calculate the Q point. And when I talk about Q point, so I talk about two parameters. That is what? That is output current, which is known as ID, right? And what? And second is output voltage, which is VDS. Output voltage, that is VDS. And based on this particular point, we actually are able to see that where our Q point is and at which particular region our JFET or any transistor it is operating. Either it is operating in cutoff region or saturation or maybe in linear region. So based on this particular Q point, we are able to judge where our JFET or any transistor it is operating. So that's the reason why we focused on DC analysis, right? So now what we generally do in DC analysis is that we biased the transistor. We bias any transistor, right? Great. So I hope everything is clear up till now. Okay, up till here. Now we are dealing with AC analysis, and in AC analysis we deal with amplifiers. Okay, in AC analysis we deal with amplifiers, right? So for that we need to model any transistor. If you could remember, in case of bipolar junction transistor, we had done three modeling techniques, or rather we had seen three modeling techniques and they were as follows. That is, first of all, very first time when we wanted to model the bipolar junction transistor, we focused on the hybrid pi model. But before that, we actually focused on two-port network, right? We actually had dedicated, I think, more than R for each and every parameter, like Z parameter, Y parameter, ABCD parameter. Then we had also seen that H parameter was significant over all of those parameters, and then we use H parameter, H modeling of bipolar junction transistor. Then we also saw T modeling, and then at the end I told you that R pi model is much more significant when it comes to high frequency analysis. So we also saw R pi model, right? So we saw three modeling techniques of bipolar junction transistor. So similarly, in case of JFET, we are going to see one modeling technique. And if you could remember, I told you that BJT was current controlled current source, and over here you can clearly see in case of JFET, we are changing the input voltage, and thus the current is getting changed, right? I hope you are getting this particular part. If you could remember, ID was directly proportional to the inverse of VGS square. That means ID, if you could remember, ID, it is equivalent to what? IDSS into 1 minus of VGS by VP the whole square. So basically it is proportional to the VGS square. So if your input voltage is changing, so your ID is also changing, right? Great. So everything is crystal clear up till here. Great. So let me proceed further, and before going to the modeling technique, let me highlight few of the things. So this is our gate, drain and source. And we all know the internal structure of JFET. This particular part, it is internally connected, but I had not shown to you. It's fine. I hope you all guys will understand it, because we had discussed this particular part. Any which ways, we'll just focus on these three terminals. It is source, gate and drain. So we all know there is one n-type region in between, and it is sandwiched between two p-type region. So one p-type it is available at gate, right? The n-type it is available at drain and source, if you could see very clearly. So what we do is that during DC biasing, what we generally do, we provide negative voltage to the gate and positive voltage to the source. That means your VGS is negative, okay. And how it is negative, or rather how we are able to achieve this? Due to DC biasing. So let me write over here, during DC biasing, just a second, let me, yeah, during DC biasing, we keep VGS negative. This we had already seen, right? During DC analysis, we keep VGS negative, and with the help of superposition theorem, whenever you are dealing with AC analysis, right? So we grounded DC sources. This is the basic part we had seen in the case of this BJT as well. This is a simple logic of superposition. If you are dealing with one source at a time, you should ground the other source, provided that source is voltage. If it is current source, so you have to open. I mean, you have to replace that particular sources with its internal impedances. So we all know internal impedance of any current source is an open circuit, is an infinite resistance, right? And internal resistance of a voltage source is I mean, it's 0, right? I mean, it's grounded directly. It is represented with short circuit, right? Great. So everything is crystal clear up till here. So basically, when we are dealing with AC analysis, so we ground the this particular part, I mean this one. So let me come to that particular part, but before that, let me highlight this particular part once again. So as I written over here, I mean, I'll provide negative voltage to the gate and positive voltage to the source, and at the end we can clearly see that my VGS, it is negative, right? You can clearly see my VGS, it is negative, right? Great. Now let me proceed further. Alright, so sorry, I'll come to this particular part. I think I just forgot to erase this particular part. Yeah, any which ways, we'll come to that particular part later on. So I know now you'll ask me one question based on this particular thing, that why exactly we are taking positive over here and negative over here. Let me come to that particular part, but before that, again, let me write over here, this is my gate, right? And this is my source, and this is my drain. So you can clearly see source is common to drain and gate, right? Source is common between the input and output. Since we are dealing with common source amplifier, as I had already told to you, that in common source amplifier we make source as common terminal. So you can clearly see this is my source terminal. Let me take yellow color. Yeah, so this is my source terminal. It is common to drain, it is common to gate, right? Great. So that means what? This is my gate, this should be my gate, of course, because over here you are taking input and over here you are taking output, so this should be my drain. Great. Well, now as I told you, all the DC sources are grounded, right? But now you'll ask me, then why exactly we are representing gate and source with open circuit, and why exactly you had written plus over here and minus over here? So there is one strong reason for it. See, with the help of DC biasing, what we are doing, we are providing negative voltage to the P side and positive voltage to the N side. So basically we are making we are actually reverse biasing these two diodes. If you could see very clearly, these are two diodes. We are providing positive voltage to the N and negative to the P, so basically we are reverse biasing these two diodes. If you could see very clearly, they are acting as a diode. Okay, so due to reverse biasing, what is going to happen? The depletion layer will increase and the current flowing through the gate, I mean the current flowing between the gate and source is 0, and since my IG is 0, okay, my IG is 0, so therefore I can write it in this way. We all know resistance. Let's say for example resistance is RG, it is equivalent to VG by RG. Forget about what VG is, our IG is 0. This is what we know. And why IG is 0? Because the gate and source terminal, they are connected in reverse bias condition, and my IG is 0, and whatever the value that might be present over here, let's suppose that is X, but my resistance RG would be infinite. I hope you are getting this particular point. Whatever the value of VG might be, but since my IG is 0, so therefore this particular thing, that means this particular part, gate to source terminal, I will represent it with the help of open circuit. Why open circuit? Because rather than representing one resistor over here and then writing that that this particular resistance has the value as infinite, so it doesn't make any sense. So infinite, that means it will act as an open circuit. I hope you are getting this particular part. Everything is crystal clear up till here. Great. Alright, so now I will come to this particular part, why I am taking positive over here and negative over here. I know most of the students will face doubt over here, because these two things are absolutely contradictory. You can clearly see I am taking negative over here to the gate side and positive to the source side, but I had done something reverse over here. And the reason is quite simple, because during AC analysis the DC is grounded, right? So that means I'm just providing AC signal over here. So I'm just providing AC signal over here, positive, negative. So this is my AC signal, right? AC signal. So how I'm representing AC? Positive up and negative below, right? I know, I mean AC the polarity of the AC signal changes, but generally if you are working theoretically, so this is how we generally represent voltage: positive side up, negative side down. Okay, I hope you are getting this particular point. And therefore whatever the signal that you are providing to the input side, the same signal will reflect between the gate and source. I hope you are getting this particular point. So basically this particular signal, it is following this one, and it is following this one. So that's why I'm representing it as positive and negative. I hope you are getting this particular point. Okay, it is nothing but the AC voltage. I mean, if I'm providing AC voltage, so that particular voltage would be getting reflected over here. Okay, and over here the voltage drop between gate and source, it would be VGS. Voltage drop between gate and source, it would be VGS. Great. Now coming to this particular part, drain and source, we all know that there is one current flowing between the drain and source. Okay, and that current is constant, that is ID. That current ID, it is constant, which is flowing between drain and source. It won't lose any, ID won't lose anything. Why? Because you can clearly say ID won't flow in this particular direction. Why? Because you can clearly see ID will only flow in this particular direction. I mean, I had explained that particular reason. I will not explain that particular part. That is the internal structure of the JFET. We are actually applying certain voltages, and due to that particular reason, what are the electrons that are available, they will only flow in this particular direction, and eventually based on the direction of electron, the current will always flow in the opposite direction. So that's why the current will flow in this particular direction only. Okay, all right. So how I'm going to represent this particular current? See, whenever I am talking about AC analysis, and when I talk about representation of current, so let me just move it little down. So if I want to represent a current source, I will represent it in this way. See, I will represent it in this way when I am talking about AC analysis. And the moment I represent the current source, I will also represent one resistor. Now you will ask me why. This particular reason I had explained in case of bipolar junction transistor course as well. This is because the internal impedance of the current source is infinite. So whatever the resistor that you are applying over here, ideally its value is infinite, but generally it is in that its value is in around 50 to 100, or even more than that, 50 to 100 kilo ohm, but generally it is 50 to 100 kilo ohm. Okay, so that's why if you could see very clearly over here as well, to represent this particular current ID, we had represented it in this way. See this particular part, see this one, between drain and source, right, between drain and source. So you can clearly see this is how we represented this particular value. I hope you are getting this particular part. Great. So now let me erase all of the thing. All right, so now let me move it little above. All right, great. So this is my current ID. Okay, this is my current ID. So what I told you all guys, my JFET is what? JFET is voltage current, just a second, voltage control current source, voltage control current source, right? So if I like how I should represent that. So to represent this particular current source, I need to show that this particular current source, it is dependent on the input voltage. I hope you are getting this particular point. See this particular current source ID. So this particular current ID, for time being I will write ID. So this particular current ID, it is dependent on VGS, right? But let's suppose if I'm just writing ID. So with this particular representation, I'm unable to see that this particular current ID, it is dependent on VGS. But now if you could remember one formula, that our transconductance is nothing but what? ID by what? ID by VGS, right? So therefore, can I write ID as GM VGS? Yes, of course I can write it in this way. Therefore ID would be equivalent to GM into VGS. So sorry, this is VGS, my bad. So this is GM VGS. Okay, and therefore just to make sure that, just to show the so that this particular model, it is representing voltage control current source. That means my current will indicate that there is certain component of input voltage that is present at the output side as well. That means my current is totally dependent on the voltage which is present at the input side, right? Your voltage is controlling the current. That's why it is known as voltage control. Voltage is controlling what? Voltage is controlling this particular current source. I hope you are getting this particular point. So that's why instead of representing it as ID, we will represent it as what? We will represent it as GM VGS. Great. So this is GM into VGS. Okay. So let me just keep this particular point over here. Okay, this is how we actually derived this particular equation. Okay, so whenever you will refer my PDF, you can easily note it down. Okay, let me erase this as well. No need. Yeah, this is voltage control current source. Okay, and of course, as I told you, whenever I represent a current source, so there is one internal impedance present with that current source. Generally it is infinite. I mean, ideally it is infinite, but generally its value would be in few kilo ohms, that is 50 to 100 kilo ohms, right? It totally depends on lots of things. I mean, there are a lot of things that is on which this particular resistance depends. I'll explain that particular part maybe in some another video. No need to explain that particular part over here. That is not at all related over here. But just remember, whenever you represent current source, although I had explained that particular part in the BJD course as well. So whenever you represent a current source, so the moment you draw this particular symbol, you have to draw one resistor as well, indicating that the internal impedance of this particular current source is infinite. This is the concept related to network theory. Okay, you don't worry about this particular part, but as of now, just remember this is RD. This is the internal impedance of what? Of a current source. Okay, this is also known as dynamic resistance when we are dealing with transistors. So let me write over here. This is nothing but this is a dynamic resistance. Okay, so this is dynamic resistance. Dynamic resistance, right? This is the current ID. Okay, this is the input voltage VGS. Okay, and why I had written plus over here and minus over here? Because we are dealing with AC analysis. That means I will connect AC signal over here, that is in this way. This is plus, this is minus. So this particular plus sign will be reflected over here. That means whatever the signal, it will be whatever the signal that is generated over here, it will travel in this way. I hope you are getting this particular point. That's why we draw over here plus and minus. Okay, otherwise you will get confused between this and this one and this one. Okay, so don't need to confuse over here. This is based on the DC biasing. Okay, and we are dealing with AC analysis. Okay, great.